So we have a lot of residential and commercial buildings. Starting with New York area, we are the structural engineers of 432 Park. 432 Park is Rafael Vignoli's building. The architect is Rafael Vignoli. Client, our developer is Maclo Development. It's a 90-story, roughly 425-meter tall building. And an important thing is the slenderness ratio. Also, it's 1:14. Another project of ours is Beekman Tower. Is Frank Gehry's building. I think Frank Gehry's only tall tower so far. It's 1:10 slenderness ratio with the 265 meter tall. Then we come to 157 West 57 building. This is the first building that we have worked in 57 line, also known as Billionaires Row. This is one street below Central Park South. So this row has a lot of tall buildings facing Central Park, which is a premium building, premium area. So 157 West 57 is 75 stories and 1,000 feet, roughly 300-meter tall building, and it's the first installment of the Billionaires Row buildings. Another prominent building by the Columbus Circle is a Time Warner Center. I wanted to show you this because this building has concrete still has them. It is a mall, it is a hotel, also it has residential floors. So there are 4 different usage of the building. It's 230 meter tall and it's been completed around 2002. Another of our buildings, the latest installment in the 57th Street line is 111 West 57th Street. It's 434 meter tall, and as today, it's the tallest, it's the most slender building in the world. It's finished, it's occupied. People are start living in there for a while now. And this is the latest installment that we have a chance to finish in the 57th Street. We have another building I would like to show. This is the first slender, real slender building that we have worked on. It's One Medicine Park. It's been in use close to 15 years now. Our client is related and architect is Sestra Rudy. It's 190 meter tall. I want to show this is another building of us. It's American Copper building. It's by the East River. It's 2 towers connected by a bridge. And maybe the picture is not very clear. If I have to go back, I have another slide in the later on. The buildings are sloping in each way. So one building is sloping, it's a long side, the other building is sloping its narrow side, and the 2 buildings are connected by a bridge. This is another building of us. We're very happy to work on this project. It's a prominent project. Architect is Harzak Dedemarang. It's a building also known as a Jenga building. It's a very special, very challenging building. And it took us a lot of time to specially engineer this building because of the shape. The building is full concrete. All cantilevers that you see is all Verandale trusses and big cantilevers. And the idea is having separate houses in the skyline of Manhattan. It's one of our buildings is the product. This is finally finished. It's 217 West 57th Street. As today is the tallest residential tower in the Western Hemisphere. And they start selling apartments, and the triplex is for sale for $250 million. So it's a very successful project. And we're very happy and proud of working on this project. Another project is MoMA Tower. This is another bit prominent architect, Jean Nouvel. It sits on extension of the MoMA Tower. So the lower 10 stories are belongs to MoMA Tower, so above is residential and below is a museum. It's 320 meter tall. It's another tall building. It's the other important thing about this building is it has no horizontal slab, so it's a roof. So we had to go through the building department just to get to include the roof definition, just a triangle. We are also engineers of World Trade Center. The World Trade Center complex has 4 buildings, and we engineer 1, 2, and 3. 1 and 3 World Trade Center are designed and built. The second World Trade Center is designed. We designed it for 2 times for 2 different architects. They are all office buildings. And the Tower 2 is built up to ground floor. They are waiting for anchor tenant to continue the finishing up the structure. So World Trade Center is today with the antenna is the tallest structure. It's 540 meter tall, and it has a special meaning for us. And obviously we have been working extensively for this project. And with this project, we first time use very high strength concrete. So using in this project, we had to update a lot of New York City code requirements. And not only wind, we have to also address seismic considerations too. This is World Trade Center Tower 2. This is one of the 2 designs. This is a design that originally engineered. This is a diamond shape it is, but it hasn't built yet. It just builds up the ground floor. It's also an office building. This is World Trade Center Tower 3. It's a Richard Rogers building. It's been built. All these buildings are occupied already. They are very significant in the New York City skyline. This is the last one I want to show you. This is 425 Park Avenue. This is an office tower. It's recently finished a year ago. It's Norman Foster's latest office building. This is 3 Hudson. This is one of the buildings that we engineer in Hudson Yards complex. Basically, this building sits on a train yard, a train parking yard. So we have 8 buildings in there right now, as today, and all these buildings sit on the train yard. So there's a platform. We engineer the platform. We engineer the buildings above them. And this building is starting soon, but the rest of the buildings are already in place. So we are also engineer high-rise buildings in international. Shard is one of them. I will pass this buildings a little bit faster. We engineer also Nakil Tower. Some of the projects are, although they're engineered and they have some level of structure in it, some of them have a foundation in place. In like the one in I will show in India. So we also have a few buildings in China. This is the building that we extensively engineered for a number of years, and it's been built only the foundation level. This is under construction right now. This is Atlantis 2. This is in Dubai. It's a very interesting structure. This is another special structure. It's a museum, Sheikh Zayed Museum. And this is Torre Mayor, and maybe you're familiar with this project. This is one of our, I think, the first project in Mexico, and we have several patents on the outside diagram system as a company for this project. And we have another engineer, another Reforma 509. I'm just going to pass this fast so we can start talking about the engineering. Okay, so why taller, why more slender? The biggest thing is the land scarcity. The location of these are, most projects are in the premium locations, and some of the city regulations with the zoning, they don't allow you to build more than a certain floor. So what happens is although there are some restrictions, places like in New York, you can buy your neighbor's air rights. So what it means is you can buy your neighbor's right to build height. So you can combine them and just add it to your building. Majority of these buildings are built that way. And so this results also cantilever buildings like 217 West 57th Street, which means is they bought the air rights of the next building so they can cantilever on top of it. It's the cantilever almost like 30 feet, is 10 meter. Cantilever for a tall building is a significant number. So this is a kind of development of how the buildings evolve along the years. And these are all our buildings. And this is basically shows you how these buildings are starting to evolve. Majority of these buildings are built in 2005 to 2018, 2012 corridor, designed and engineered. So what is slenderness ratio? This is a very important topic. Slenderness ratio, there are codes and there are documents that define this. Like in New York City, the slenderness ratio of the building is defined by 1 to 7. So if slenderness ratio in each direction, the ratio is more than 1 to 7, the code requires you to take additional steps. It's additional steps with the engineering, and also it has some mechanical requirements. So what we understand as today is, since we have a lot of buildings that are very slender, we generally call a building around 1 to 10 slenderness a slender building, and super slender is larger than 1 to 12. And as today, we have a 1 to 24 is been engineered and built and occupied, but we have other buildings, few other buildings that we engineered, not built yet. So it's just a small concept. We get this information slide from the Skyscraper Museum. That's in New York, just to give people an idea what does that mean, slenderness. So basically, a ruler, typical ruler, it's 1 to 12. And you see World Trade Center, original World Trade Center is 1 to 7. And 432 Park is 1 to 15. Then we have 111 West 57th Street, which is 1 to 24. It didn't fit, so we kind of do it this way. So there's another slide that shows the height and slenderness ratios. Slenderness ratios are very important because it changed the behavior of the building significantly. And this is one of the aspects that we look at in our buildings. Not only how tall is it and where is it and other considerations, we especially look at how slender is the building. And there are some certain things that increase when the building is slender, even the same location, same height with another compared to another building. And these issues has to be addressed early in the process of engineering. And there's another slide showing our buildings. So this is a document from one of the magazines in 2014. And everything is, you see, it's that time it was under consideration, that were under planning, it was on the sketchbooks. Architects and developers were discussing this, and we start engineering all these buildings. This is the 57, maybe I can show. So it's the 57th Street, where we call the Billionaires Row, and in that area, this is the most expensive real estate area because of the view of the Central Park. And as today, all these structures are built. So the one you see on the right side is 111 West 57th Street. Next one is, okay. This is 111 West 57th Street, 157 West 57, and this is 217 West 57th Street. This is another view. This is all these projects are in under construction in 2018, and this is 432 Park. This is another view of steel erection for top of the building for 111 West 57th Street. This is Chrysler Building, this is Momo Tower, and this is 157 West 57th Street. This is another view. You see at the top of the building here, this houses the TMD and mechanical floors, and above is a steel structure with openings in them. And next one is 157 West 57. It has a slush tank to control the comfort levels. It has 3 stack slush tanks on top of each other, and this is Momo Tower. This is another view. And this is 217 West 57th Street when it's under construction. And as today, all these structures are built, and this is the skyline when you look at from Central Park to Central Park South, downtown Manhattan. So what we look at when we design a structure, we look at with the architects and the owners, we try to maximize the utilization of the available space. So what it means is we try to let owner to increase the sellable area. So we try to get a good product, and we are part of the team with the architects and the developers. So our first goal is having a successful product. We try to do an efficient construction. What it means is labor, in the markets that we work, labor is very expensive, and it's hard to work. It's in the middle of the city, and it's a very touristic area. It's not an easy thing to even transport anything. And there are some local regulations, like you cannot pick up any foreign work with a crane above the street. So there are some other restrictions local to certain markets. What we design is we think about the efficient construction, and it allows us to, any of these buildings that you see in the presentation, to build every floor in 2 to 3 days. Even the structure is, how hard is the structure, or how complex is the structure, because none of the two structures are the same, but we have been doing this for over 20 years in our projects. Obviously, doing a 30-story building with 2-year cycle, a 2-day cycle, every 2 days you pour a floor, is different than when you do a structure with 1,000 feet or like say 100, 120-story high buildings. But we achieved that, and we are happy, very happy with the results. There are some additional constraint comes with the fast construction. There are creep and shrinkage effects that has to be considered, taken into account. This we address it all in the project. Also, very important, I should have put this in first, every structure has to be safe, and that's the most important thing. And also, we look at some other service life conditions. What it means is we look at deflections. Also, very special to tall towers and residential and office towers are, we look at accelerations on the buildings, which is a comfort criteria. Some of our designs are basically governed by accelerations too. So every project has a different geometry, different architect, different characters. So we address every structure in a different way. I want to show a few of our projects. It's not basically a rectangle or a square. It's different challenging projects with the architectural view and architectural intent. Also with the developer's final product. So this is one of our proud projects. It's Momo Tower, 53rd West 53rd Street. It's 1,000 feet, almost 320 meters tall. It's 82 stories. The special thing about this project is a core of this project is eccentric to the building. So there's no central core. The core is on the eccentric side, which you have no view. So the core is on looking to the south, north is looking for to the Central Park. Every floor The north and south is sloping. So what it means is every floor you have to slope every column. Also, we have a concrete diagram system. So, let me go back. Okay. So we have a concrete diagram system. When we first start the project, as we always do, we meet with the owner and the architects. When you're looking at the first phase, there are a lot of concrete connections in there. So we discussed having a steel structure, concrete core steel structure, but steel was expensive at the time of the construction, the development. So they decided to go with concrete. It was a pure monetary decision because as an engineers, we try to address the connection details with the diagrams. We don't want to make the building more complicated than it is, but the decision was made, and this is the full concrete structure, as you see, with the diagrams, with the floor core, and the sloping columns. There's another one, another geometrically challenged project. It's 56 Leonard. Also, I repeat, it's a Jenga building because none of the two floors are same at the top of the building. There are a lot of cantilevers, there are a lot of verandal trusses in there. The owner again insisted on having everything on concrete, and we provide a concrete structure. 217 West 57th Street, we have, I mentioned before, we have a 30 feet cantilever here on the existing top of a building. This is, that's what I wanted to show before. This is American Copper buildings on the east side of the New York. So in this one, we have this bridge is not a passing bridge. It says a amenity space. So it's a two-story structure. It has a pool. It has a gym. It has a common area. The owner wanted to have one amenity area for two buildings instead of two separate amenities to save money. And this is the solution that we come up with. So the bridge that you see today is cantilevering from one structure and on rollers on the other structure. This is when it was under construction. So this building is sloping along the long line, and this building sloping on the narrow side by design. So we have a lot of calls on the construction. When I was on construction, people saw that building doesn't have a straight shape, so they called the building department saying something's wrong with the building. So we had a lot of stop orders to just make sure that nothing is out of control. But this is by design. This is just architect's view. In this building, it's very interesting because and this portion is steel. In this building, we achieved in both towers a 2-day cycle, although everything was shifting every day. And 111 West 57th Street, this is one of the most challenging buildings because the space is very tight. Basically, the width of it is, if you see in the movies, you have townhouses in New York. The width of this structure is basically 2 townhouses. It's not more than that. And it also sits on Steinway building on 57th Street. So it's not only a brand new tower, it was also rehabilitation of the existing Steinway building. And we have to go through the existing Steinway building, which was built, I think, 1800s, yeah. This is one of the objectives I was telling. So what we try to do, we try to have a simple structure. Simple structure means no interior columns. We have a perimeter structure here, works with the core, and we have no interior columns on this project. This is a floor plan for 432 Park. This is one of our analysis models for deflections. So this is basically the structure, main structure. You see there's a core, there's a perimeter mount frame, every floor. And also one thing is the columns on this project are exposed and they have a color. So they are white color, exposed concrete, and it's 1,400 foot tall. New York is very the weather, the temperature changes very significantly in New York. So what it means is you have to adjust your structure, design your structure also temperature load. Sometimes this temperature changes. It's defined in the code, but sometimes this temperature changes becomes like 60 Fahrenheit, which is a big number. This is a floor plan for MoMA Tower. So let me go back. So the core is here. Okay, the core is eccentric, and north side of the building and south side of the building slopes throughout the building. North side of the building faces Central Park here and here, and south faces downtown. So in this building, there's no, as you see, there's no interior columns throughout the building. And these are basically diagrams. Shows you diagrams. These columns, but they're diagrams. Yeah. So what we do with the design strategy is we look at we have to make sure that the building is safe. We have a load path, and these are all clear, defined at the starting of the project. We carefully model everything and analyze. We do extensive analysis for our structures. We understand, and because these are very important when you're starting to have a successful project. If you don't know what you're going to have in terms of sizes, or if it's not constructible, these are very important items that has to be decided and has to be agreed, because there's a this is a product at the end of the day, and there's a monetary portion of this discussion. And as we did in Steinway Tower, we have retrofit and rehabilitation also. So we look at structural system, we look at the stiffness and strength of the building, load path, we size the members, and also whenever we need it, we entertain the idea of if we need additional system like a damper for comfort, or any other geometry changes that we asked or we advise the client to do, and sometimes architects are happy to entertain this, sometimes they don't. But these are the items that we bring up to the table. So this is, simplicity is the most, one of the most important items. This is basically the structure that you see is in the MoMA Tower. This is the core that, let me go back. Okay, so this is the core, main core, and we have a external diagram system. Our core is eccentric, and we have here we have an outrigger floor, which is also a mechanical floor to control the deflections and reduce some sizes. Also interior, it's very important to have a certain core size because of the sellable area. Since the core is eccentric, we also pay special attention to creep and shrinkage. As I say, when you have a small building, this creep and shrinkage may not be a huge issue, and existing practices can address this, but when you're starting to have very slender buildings, very tall buildings, you have to address these issues, or otherwise there are a lot of problems comes. You may have ended up with a slope floors, not level floors that you say. This has to be fixed. It may increase the slab thickness because the level, how much material you put in there. And also there are a lot of lawsuits because of how much energy and how much labor that you add the materials in there after the construction finish. So all our projects, we do a creep and shrinkage analysis, axial shortening, and we issue a table to correct the slab when they build the structure. So this is a view from the top. This is an outrigger floor that, if you look, we connect outside, and we have beams, they say deep beams with the openings in them, that allows the mechanical doors attached to each other whenever it's required. But the main idea is connected in the core to the outside diagram to control the building and deflection, also to stiffen up the building. Location of the mechanical floors, there are some discussions, and we advise the client. Although there are some mechanical floors in the project, multiple mechanical floors in the project, we don't necessarily utilize them.